anyone manage?
What's our pivot?
What we've got today is two things. We're extending the moment stuff. So we're looking at what happens when your rod is not uniform. What does that mean?
When
It's moving.
Not when it's moving, no. It's when
it's not equal, like
what's not equal?
The
the
tension.
mass.
The mass. So it might. So basically, what it means is its center of mass is not the center of the rod. Okay. So you can see in this diagram the weight. The weight of the rods is not coming from the center of the rod here. It's coming off to one side. And that's because the mass in the rod is not uniform. It might be heavier at one end than, or more massive, should we say, at one end rather than the other. For whatever reason. It might be density changes, it might just be thicker, I don't know. Doesn't really matter. All right. So we're going to look at what do we do when it's a non-uniform rod. We're also going to look at an example when things are not horizontal. So we've got angles involved. We've got to resolve forces. Right, so we'll rattle through those things, and then obviously you can get on and do some work. All right, so we've got this non-uniform rod, 6 meters long, a mass 12 kilograms, hangs in equilibrium, supported by two light, inextensible vertical strings, equal length attached to its ends. The tension in the first string is 88.2. Is the tension in the other string also 88.2? No. Why not? Because it's non-uniform. All right? Because if the mass was in the middle, you could say it is, right? But it's not. We don't know this distance. It says find the distance of the center of mass from the end attached to the string. So, looking at this, taking moments about the right hand end, so this end here. So we've got it. My question for you is why?
Because then we
know the length x from the.
We don't know the length
Well,
x, that's what we're
we know that the distance from the center of mass there and the tension is x.
Yeah, but we also know the full length is 6. So that is like, if I took it from the other end, the moments would be, we just know it's 6 meters, whereas this one it's x. So
we actually know the distance.
so we
Yes.
know that distance, right? But what would we not? We don't know t. If I wanted to know t, I would take the moments about this end, right? But because I want to know the x, which is the distance from that end, I need to take moments about this end. So do you remember I asked you last time I saw you to really think about which point you're taking moments about, because there will be times where, for instance, obviously it won't appear on the video, but we were doing a question where there's a rod like this and it had several pins holding it like this in equilibrium, and you have to decide which one of those you're going to take moments about. And one of them will give you something you can solve, the other two will give you things that you can't solve. Right? So it's about making those decisions. So what have I done here? So I've taken the right hand end because that gives me an equation 12g, or an expression 12g times x. What is that? So that's the anti-clockwise moment of the 12g around this point, yeah? Right. And then that is equal to 88.2 times 6. The 6 because that's the length, and it's going in the opposite direction, and it is in equilibrium. So I know this side equals that side. So you can now calculate x, no problem. I'll let you do that. All right, so the next one, you're going to look at it and go, that's a lot to look at.
Okay, do it, Reggie.
So we've got a non-uniform rod. So this weight is not in the center. The mass is 10 kilograms, so we've got 10g. Length is 6. Has a center of mass that is from 2.5 meters from the end. Okay. It rests in equilibrium on 2 supports, which are 0.3 meters in either end. A particle with a mass of m is placed 1 meter from the support closer to end B. Given that the reaction forces in the 2 supports are equal, all right, find the value of the mass. So obviously this mass is such that it counteracts the weight, yeah, to make the reaction forces the same. All right. So, to start with, I've looked at the forces on this plank. Why is 10g plus mg equal to 2r?
Is that the second one? Forces have an opposite and equal.
Yeah. So we've got the downward forces and the upward forces must balance each other out because we're told it's in equilibrium. Okay. So we've done that. We know G is 9.8. So I've written an equation for R. Right. There's still 2 unknowns at the moment. So what do you do when you've got 2 unknowns? But to do simultaneous equations, you need another equation. So obviously it's on the screen, but where does our other equation come from? It says it on the screen.
mg plus mg.
Taking moments about the support closer to end A. Again, why the moments closer to end A?
Because we know just
Because you don't have 2 unknowns. Okay, so got the diagram here. What have I done? What have I identified? Direction.
the 0.3 meters
Okay.
in.
So given that diagram that I've drawn and already labelled, you can now write out any equation for me. I'm happy that you didn't try and use both R's, because obviously, why does this R on the left, why is that not included?
Close to the end, A.
Because it's on the pivot point,
Yeah.
so it applies no moment whatsoever.
So, sorry, where do you get 48?
98.
Is that, sorry.
So when I take this one here, is nothing. And you will end up with M equals. Anyone done it yet?
2.94.
2.94. Yeah. Your next thing to do this obviously would be exercise 22C, which is page 517, but we're going to go on to the next thing first. Okay, which is What happens if we change the angles? Yes.
Yeah, horizontal and vertical.
We do still have your horizontal and vertical components to each force that needs to be resolved. We did this before, didn't we? So this is what's happened. So there's kind of common ones like ladders leaning against walls and rods just hanging at different angles, that kind of thing. But yes, we're basically going from this situation where if this is the pivot point, we just have a distance. Now, I did explain to you when we first did this what the important distance is. So what did I say was important about the distance? So we've got the force, and we are looking at the perpendicular distance. So from the pivot point, right? So if we're taking moments about this point, we're looking at the direction of, or line of action of the force, and we're then looking at the perpendicular distance from the pivot point to the line of action of the force. So it's all about that T-shape or L-shape, whatever. I remember doing it with the laminas, you know, that kind of thing. All right. So, say this is the key points there. Sum of horizontal components of all the forces equals 0. The sum of all the vertical components of the forces equals 0. You've already done that in the past. But now we've got the sum of clockwise moments equals the sum of anti-clockwise moments. But we do have to consider how we calculate those moments. So, here's a question, kind of started off for you. Right. A uniform, we're back to uniform rod of length 2L, weight 50 newtons, is held in equilibrium by 4 light inextensible strings as shown in the diagram. 2 of the strings are horizontal, 2 are vertical. The rod makes a 30-degree angle with the horizontal. The tension in the vertical string to the left of the diagram is 20 newtons. Find the tensions in the 2 horizontal strings. Okay. So I've already labelled up my diagram. I'll let you draw yours and label it up, and then we can think about what we do next. But we can now say that T3 must be 30 newtons. That's why we're asked to find T1 and T2, because T3 was too easy. All right, now to start this problem off, we're taking moments about A. Why?
Because that's
Or doesn't it matter?
because
No.
Doesn't matter on this one?
No.
Why? Because
We know T3.
we've already found T3 now. We did that laminar one where we had the 2 unknowns and we weren't going to be able to find what one of them was, but we have been able to find this out. Okay, so we're taking moments about A. We'll just do A. All right, so how do we take these moments? So we've got clockwise equals anti-clockwise, but how are we going to do it? Let's look at the clockwise ones first. All right, so how do we write them? I should add in, this is 30, isn't it? It was in the diagram.
No.
So what's a moment again? A moment is equal to force times distance, but distance is the perpendicular distance. Okay. So if we take this first one, what's the force? 50. So we've got 50 times its distance. But what's its perpendicular distance? Well, here's the line of action of force. Right? Let me get this. If this is the line of action of the force, this is the pivot point. So I actually need this distance here. Okay, that's the distance I need. What is that distance? Well, this distance along the rod is L, that takes me to the center of mass. This is a right angled triangle. Okay. That's in there. We don't know L, but what can we write? This distance is right angled triangle. This is the adjacent side. So we're looking right angled triangles, we're looking adjacent angles. So we're looking at SOHCAHTOA. So we're looking at cosine. So cosine of 30 equals the distance that I want divided by L. So the distance is L cos 30. So here I can put that in there. So 50 L times cos 30. Okay. Plus what? Well, we've got this one here. So again, this is where people, this is why I'm trying really hard at the moment to really get this good for you, because this is the bit I find quite tricky, like students find quite tricky. So what we do is we take the line of action of the force, all right, and we need the perpendicular distance to the pivot point. All right, so the distance I need is actually that distance there, right?
So distance is 2L plus 30.
Is it? You sure?
Yeah.
So I could actually, this distance is the same as this one over here. So you're right, if I just extend this triangle like this instead. Careful. What distance am I trying to find? This one here, right? So this one was D1. Let's do that. This one is D2. So it's actually sine, isn't it? So it's going to be 2L sine 30. So I've got 2L sine 30. Okay, that's those two red ones done. I should have written it in red to keep it going. Now I've got the equal, well, it's going to be equal the anti-clockwise moments, which is T3. Right, this one here is giving me an anti-clockwise. So what's that? Here's the line of action of the force. The distance is this distance here. So it's adjacent again. So we've got D3. So D3 is 2L cos 30, because it's this whole length here. It's getting complicated on my diagram, but that's kind of why I'm trying to talk you through it slowly. Right? So we've got that equals to 2L cos 30. All right. By missing some things. What have I missed? The forces, haven't I? So for this one here, got so focused on distances, This one was 50 because that was this one. This one was the T2 one, so that's going to be plus T2, 2L sine 30, yeah. And then we've got the equals, this one was going the other way, so it's the forces T3, 2L cos 30. So force times distance. So we've got the forces, I feel like I'm over highlighting now, but you know, the forces are the 50, the T2 and the T3. All right. But we actually already know one of those things, which is T3. Is there anything else we can do to simplify this? Well, you were mentioning a minute ago that L was a problem because we don't know L. Why is L no longer a problem? It's common, isn't it? We could just divide through by L. It's in every single one. So I can divide through by L. Right? So then I'm just left with 50 cos 30 plus T2, I'll do a 2T2 sine 30 equals T3 is 30 times 2 is 60 cos 30. Right? We now have an equation with only one unknown, which you can tell me the answers. So, and obviously we know that T1 is equal to T2. So once we found T2, we know what T1 is. So over to you. Well, we should write it as
8.6.
Yeah. So we get 8.66 newtons. T1 equals T2, and that equals 8.66 newtons. Okay. Every time I did this, I looked at the force, I extended that line so that I could go perpendicular up to the line of action of the force. Right? And that's the thing that you have to kind of maintain. All right, moving on to one more then. Okay, I did want to show you this. I want you to draw a diagram for me, but we're not going to do the question because I want to highlight this. This is not accidental. This is as per schema work, but it's something for you to be aware of for next year, whoever teaches you. This question comes up in this bit, but it has coefficient of friction in there. Coefficient of friction doesn't come up until early next year. So you will have to come back to these questions in moments to deal with the coefficient of friction calculation. But what you can do is set up your diagram, all right, and look at the forces and things like that. All right, so have a go at that to start with. So we've got a ladder can be modelled as a uniform rod, length 4 meters, mass 12 kilometers. The ladder is placed on a rough horizontal ground and against a smooth vertical wall. Okay, the ladder is on the point of slipping. Find the angle the ladder makes. So just draw me a diagram to represent that. I'm just looking for what your fully labelled diagram would be like. What are the forces, that kind of thing. So obviously, you will have, which way around you've done it? I've done it that way. Okay. You will have a wall. You will have floor. You will have a ladder. Okay. All right. That's the first simple stuff. What about the rest of it? What do we have to put in?
It's quite the weight of the ladder.
So the
we'll
weight.
Put it in the middle.
The weight in the middle, good, because it's uniform. So we've got that going down
12 G.
12G. Okay.
It's up to you.
Okay, yeah, because the ladder is 4 meters long. Yeah.
Angles, X, roots.
So this angle, it says, find with the horizontal. So this is the angle that we are going to be asked to calculate. So where are the forces? So we've got that. Anything else?
The point of contact between the wall and the ground.
The wall and the ground.
The
ladder and the ground.
The ladder and the wall and the ladder and the ground.
Okay. So where do the forces go at this point?
Down.
Up. Because it's a reaction force, yeah? So we've got a reaction force. This counteracts that, yeah? There's no down. There's no centre of mass at the end of the ladder. This is the thing that's pushing down here and here. Yeah. So we've got a reaction force here,
And a reaction force going like
and we've
out of
got
the wall.
a reaction force going that way. So we can say this is reaction force in a y direction, this is a reaction force in the x direction. Yeah.
Is there a real one?
There's one final force.
Is it perpendicular to the ladder?
No.
This is
The other force is actually, here's the bit to do with the friction. So yeah, you'll have a force going this way, which is the frictional force. Okay. And this is what you'll get to. To work out the frictional force, you've got the coefficient of friction, which is mu, okay, times R, which is the reaction force. So in this case, Ry. Okay, so that's what your diagram. Now, so why is that a question? Well, obviously, if this is your ladder and you've got a rough surface, if I hold it up, it's not going to slip, right? So obviously, the frictional force of the table is being held, is holding it, holding the mass, yeah? But if I reduce that angle, what's going to happen? I'm going to get to a point.
It just slips.
Okay, so that's where the angle is such that the weight will overcome the frictional force, and that's what we'd be looking for. And how would we do that? You'll be taking moments again. Yeah. So this is still a moments question.
Is mu constant?
Mu is a constant depending on the surface. So in this case, mu is 0.4. Different materials will have a different coefficient of friction. I'm sure you've looked at that.
I'm guessing it states what the coefficient of friction is.
Well, so in this question, yeah, but sometimes you'll be asked to figure out what the coefficient of friction is based on the fact that it's, in this case, it says the ladder is on the point of slipping, which means if we go any further, it goes, and that means that the force balances with coefficient of friction. All right, so I just wanted to point out this is one of the worked examples, so I didn't want you looking at that going, oh, I need to be able to do that at this moment. So looking at exercise 22D, all right, exercise 22D, which is on page 520. Some of the questions you'll be able to do because they have nothing to do with friction. But those that say friction, sorry, Anish, let me know when you're finished and I'll carry on. I'm a YouTuber, desperate to know. Are you done? Okay. All right. So some of the questions, because you're obviously going to go away now and do some practice, aren't you?
Yes, sir.
All right. I don't need to give you any more prep. You're just going to do some of this moment stuff. So what two exercises are you going to work on? 22, C and D. Okay, I'm just giving you those. What are you not going to worry about in 22D? Any of the, let's say, coefficient of friction. Okay, been a pleasure.